So, this is our second lecture on calculus of Rn. So, since we will be dealing with the space Rn, so I will recollect what Rn is. So, set theoretically, Rn is the set of all n tuples of real numbers. Each ai is a real number. Now, there are some special features of Rn. One of the important feature is that here you have a coordinate system. So, I am defining these n real valued function x1, x2, x3, xn. These are n real valued functions. And these functions are such that if you pick any of them, it will be a function from Rn to R such that xi operating on any point of Rn gives you its ith element ai. These functions I will be calling as coordinate functions. So, these xi's are called coordinate functions, or sometimes we also call them as slot functions. So, these coordinate functions are always available to us whenever we work in Euclidean space Rn. Now, if you think of functions, in my last lecture I talked about the calculus of one variable, that is when you have functions from R to R. What is the derivative, what are its characterizing properties, etc. Now, as a step forward, I will be dealing today with the functions from some interval a b, which is in fact an open interval, into say R m. So, you can see that if I have a point t over here in the interval a b, then f t will be a vector of R m. Being a vector of Rm, it will have components. So, here f t being a vector of Rm will be written as this f1 t, f2 t and so on, fmt. You can easily see that these f1, f2, fm, they are real valued functions on the interval a b. And if you look what these functions are, this for example fi will be nothing but xi composition f. If you compose f with the slot function xi, you will be getting a real valued function on the interval a b defined like this. So, what you need to keep in mind that every functions on from interval or whole R onto Rm will have these m component. So, this is to be kept in mind. All right. Now, come to the definition part. So, definition is the same. So, definition of the derivative of a function from R to Rm. Now, if f is a function from an interval a b into Rm, then I can think of the quotient of this. Suppose p is any point over here, a b. Then if this limit exists, f of p plus something h minus f of p upon h when h tends to 0, if this limit exists, we say that f is differentiable at the point p. We say f is differentiable. We say f is differentiable at p. The definition is same as you had in case for functions from R to R. And you see this is meaningful also. F of p plus h, f of p, all of them, both of them are vectors of Rm, and this vector is being divided by a scalar h. So, this remains meaningful. The limit is also meaningful. So, this is called the derivative. And this limit, suppose it is equal to f dash, I will be denoting this limit by the symbol f dash p. Minus f of p upon h, h tends to 0. This limit is called the derivative of f at p. So, this is derivative of f at p. All right. So, this is the definition part. Now, we want to extend it for functions from Rn to Rm. So, in order to extend this definition for functions from Rn to Rm, we need to look at some of its characterizing properties. Last time we had an observation about this derivative, and the observation was the following. I will write down this as a theorem. So, okay. So, the observation was, which I am writing as a theorem. This is the first theorem. And let me write down first. So, f is differentiable at a point P of the interval AB if and only if there exists a linear map. Let me call it LP from R to Rm such that f of p plus h minus f of p minus LPH upon h in the limiting case, this is equal to 0. So, this is the characterization for a function to be differentiable at the point P. If there exists a linear map from R to Rm such that the limit of this quotient is 0, then function is differentiable. So, every characterization is as good as the definition. So, we can consider this as the definition of a differentiable function.
We have discussed in lecture 1 also this thing.
Yes. Now, the same thing holds for function from R to Rm. What you can see, the proof since we have already given in our first lecture. So, what you can see, number one observation, that you can take it as a proposition that the linear map if I call this as formula number 1, the linear map LP defined in 1 is unique. The proof is easy. Suppose there are more than 2 linear maps satisfying this condition, take the difference of the 2, you will notice that this LP will come out to be unique. Now, since it's a linear map, it must be defined as LP is linear. It must be defined as LP operating on some real number, say h, is equal to sum A into h. This is how a linear map is always defined. I emphasized this thing in my last lecture also. Whenever you have a linear map from Rn to Rm, then it will always be defined as Tx equal to A into X, where A is a m by n matrix and this is a vector of Rn, you may call it n by 1 matrix, and this product is the matrix product of the two. This is how a linear map is defined. So, since we have a matrix, since we have a map from R to Rm, so A must be a m by 1 matrix, or you may call it a column vector, and this H is a 1 by 1 matrix. All right, and this product is still the matrix product. So, matrix product or it simply is scalar multiplication of the vector with a scalar. So, this is how LP is defined, but what A is, that you can see. In fact, in my last lecture you had seen that this is in fact the derivative. Okay. Since I was talking about the derivative here, let me recall what this A is. In fact, if since f is a map from here to here, here m is greater or equal to 1. In fact, the case of one dimension is also taken care of. So, if f of t is equal to say f1t, f2t, or you are taking point P, so you better take it P, f2p and fm, and if you take f of p plus something say h, so it will be f1p plus h, f2p plus h and fmp plus h. And the difference of the two, that is f of p plus h minus f of p, is equal to pointwise difference p plus h minus f1p, and last component will be fmp plus h minus fmp. And when you will divide this by h, all components will be divided by h. This is how you multiply a vector by a scalar. And when you will take the limit in the left hand side, this limit will go to each of its component. Now, if all these components f1, f2, f3, fm, they are differentiable functions at p, then these derivatives you can denote by f1 dash p, f2 dash p and fm dash p. So, if you call it f dash p, then you see that f dash p is nothing but this m by 1 matrix. I am writing as a row vector, but I should write down this as a column vector. So, this is what the derivative is, and if you want to see it, so what else you will say over here, that a function is differentiable at the point P from AB to Rm if and only if each of its component is differentiable at P. So, that is an important thing that you should keep in mind. Now, if you want to see this vector f dash p, you can see it. Suppose, let me draw the graph over here. So, I am considering functions from interval to Rm. So, let me draw an interval AB over here, and suppose this is R3. So, I am drawing the graph for R3. So, f is this function, and image of this interval under the function f will be some curve in R. Okay. And if I take a point P over here, so its image will be somewhere here. So this is the vector Fp. And if you choose a point P plus H over here, its image will be this vector Fp plus H. And the difference of the two, let me call this point on the curve as A and this point as B. The difference of the two will be a vector AB, which you can say it is the chord of the curve. The curve is the image of the function from interval into R3. So this is f of P plus H minus f of P upon H. Upon H will also be a vector in the same direction, and when H tends to 0, in the limiting case, what will happen? The point B will tend towards point A, and the chord will go on like this. So the next stage will be this, it will be this chord, next will be this, and so on. When H tends to 0, it will become this vector, you call it a tangent vector, and which you say is f dash p. So actually you can see in this case f dash p is a vector. So the derivative of a vector valued function is a vector, whereas in the earlier case when you had functions from R to R, the derivative was just a scalar. Alright, and when you will move from here to functions of Rn to Rm, you will say it will no more be a vector, it will be a matrix. Okay. So we are going step by step towards the most general case. Alright, so what I was talking about was the linear map LPH, which is in fact A times H. Last time we noticed that this A is actually the derivative. So this A, you can check it up, that A is in fact f dash p, the vector f dash p. So LPH is in fact equal to f dash p into H. Now since this LP we have just seen is a unique linear map, we will be denoting it by DFP. So DFP H is f dash p into H. F dash p is a vector of Rm, H is a scalar, so DFP is defined in this manner. And we call this fellow the differential of f at p. This is differential of f at p. And this fellow, as I told you, is called the derivative of f. At p. So you can see these two objects are different. One is the linear map, differential of f is a linear map at p, whereas f dash p is the derivative. So derivative is nothing but the matrix of the linear map DFP, which we are calling differential of f. All right. Okay. So here we are. So the defining relation becomes, whenever a function is differentiable, you have f of p plus h minus f of p minus f dash p into h, which is DFP. Earlier I was writing it as LP. This limit is 0. So a function is differentiable if and only if there exists a linear map defined like this, such that the limit of this quotient is 0. This is my new definition. All right. Now, this further, now if you look at this closely, you can further see, let me denote this f of p plus h minus fp by the symbol del fp. Last time also I was using the same symbol, and this thing you may call it the change in f. Change in f when you go from p to p plus h, when p moves to p plus h. Change in f when p moves to p plus h, and this is the actual change, or sometimes we call it a non-linear change, because usually the functions are non-linear. When function is linear, the differential is trivial. So we talk of non-linear change in f. And you can also look at this fellow dfp, f dash p into h, which you have been denoting by dfph. This I will call a linear change in f. When p goes to p plus h. You can convince yourself by looking at the graph. I had just drawn the graph. This is fp. Here you have f of p plus h, and these points were denoted by a and b. This is the difference delta fp h. All right. You had also seen that dfp, the f dash p is a vector like this, and when you will multiply it by h, it will remain a vector in the same direction, little smaller or little bigger, but it will be in the same direction. So this is dfph. What this definition says, that this difference, if I write down this expression over here, it will look like this: dfph minus dfph, and delta fph minus dfph upon h in the limiting case is 0. This is what we have been saying over here. Okay. So the difference between the two is this quantity. This is the difference between the nonlinear change and the linear change. If you call this point as C, so what we are demanding for function to be differentiable is that this difference CB must be 0, must tends towards 0 faster than h. You see, if the limit of a quotient is 0, that means the numerator goes towards 0 faster than the denominator. So in fact, for differentiability, we are demanding that this fellow should tend towards 0 faster than this fellow in the denominator. All right. So this is equivalent to saying, so what we conclude is, the conclusion is that if f is differentiable, in fact this is true from both sides, f is differentiable at p if and only if the difference between the nonlinear change and the linear change, in f tends to 0 faster than h. This is an important conclusion. It should be tangent to the curve and it should tend towards 0. The difference between the two should tend towards 0 faster than h. This statement is given in several other ways also.
इसमें भी हुक वो है जैसा वेट अटक रहा है इससे भी सर यहाँ पे लगा दीजिए
जो हम लगा लेते हैं
सर भी उल्टा ऐसा
अच्छा अच्छा
बाहर ही पूरा आ रही है सर इस वजह से सर
वो पॉकेट नहीं है ना
जैसे इसमें भी
Let's see. Okay. All right. So what I was telling you that you can rephrase this statement in the following. So what you have, let me write down on the top. There's delta FPH minus dFPH upon H. This limit is 0. Whenever function is differentiable, this limit of the quotient must be 0. All right. Now, if you look at closely, you can rewrite it as f of p plus h, in fact, minus f of p minus f dash p into h upon h equal to 0. So what are you saying? This thing should tend towards 0 faster than this h. This statement is written as f of p plus h. This is equivalent. This is equivalent to saying, this is equivalent to the following statement: f of p plus h minus f of p minus f dash p into h equal to oh, little oh. This symbol we also use. Or I can say that f of p plus h is equal to f of p plus f dash p into h plus oh, plus terms of the order of h. So if you look this last relation closely, you will notice that this is the Taylor series up to first order. So a function is differentiable at the point P if this Taylor series is satisfied, and the remainder term OH must tend towards 0 faster than H. Okay, so this box condition becomes the characterization for a function to be differentiable at P. All right. So I am rephrasing my statement in different technical terms. All right. Now this theorem 1, this is actually theorem number 1, the existence of the linear map, which is unique and we call it differential of f, gives rise to another function which is continuous. So this leads to the following theorem. In fact, a theorem. So in fact, theorem 1 motivates us to define a function eta p. So if f is differentiable, so for a differentiable function f, for a function f from interval a b to Rm, m is greater or equal to 1, differentiable at p, differentiable at p, we consider a function. We consider a function eta p from R to Rm. and I define it like this. Eta p of h is equal to f of p plus h minus f of p upon h minus f dash p whenever h is non-zero, and its value is 0 when h is 0. Now, what will you say? That if f is differentiable, then eta p will be continuous at 0. This is easy to observe. If f is differentiable, at p, eta p is continuous at 0. That is easy to see, because for continuity what you have to see? You have to see that the value, what you need to check over here, that the limit of eta p h when h tends to 0 must be 0, which is 0. If f is differentiable, in the limiting case this will be equal to this, and therefore it will be continuous. In fact, the converse is also true. Converse is also true. If you have a continuous function, converse is also true. Converse is also true. That means what? That means if I define my eta p h, okay, equal to f of p plus h minus f of p upon h minus a vector. Let me call it lambda p, where lambda p is a vector of Rm whenever h is non-zero and 0 when h is 0. If eta p is defined like this, if there exists a vector lambda p such that eta p is defined like this, then it will be then f will be a differentiable function. It is continuous. So let me restate. If there exists a continuous function at the point 0 defined like this, then f is differentiable at p. Okay. So if converse is also, that is if eta p defined like this is continuous, at 0, then f is differentiable. At p. The proof is easy. In fact, in this case, when this turns out to be continuous, this lambda p will be precisely f dash p. One way is obvious. The other way you can see, converse part. One way is obvious. Converse part, let us see. I have to start from here. Suppose I am given a continuous function eta p defined in this manner. So I have to consider the limit of eta p when h tends to 0. I say eta p h. Let me see what it is. Okay. This will be equal to limit h tends to 0. Look at the definition of eta p. It is defined like this: whenever h is non-zero. Since you are taking limit, so it is non-zero. So this is f of p plus h minus f of p upon h minus lambda p. Okay. Now this is continuous, so it must be equal to eta p at 0. We are assuming that this is a continuous function, so it must be there. And what is eta p 0? Look at the definition. This is 0. So what you have proved? You have proved that limit h tends to 0, f of p plus h minus f of p upon h is equal to lambda p. That is, f dash p exists. This fellow you call is as f dash p, it is precisely lambda p. So what you proved, that f is differentiable with derivative lambda p. So this becomes another definition, because the result is true from both sides. It's an if and only if result, so you can treat it as a characterization. So characterization is as good as the definition. So I will call it as another definition for a function to be differentiable at a point in AB. So I will say that f is differentiable. You can call it a theorem or you can call it a definition. This theorem is also a characterization. A function f from an interval AB into Rm, m is greater or equal to 1, is differentiable at P, is differentiable at P. If I take h into the right hand side, this will become lambda p times h. This is a vector, times h means you have a vector, a linear map. If at P, if and only if there exists a linear map, I will call it DFP, okay, from R to Rm, and a continuous function, I will call it eta p, such that eta p is a function from R to Rm once again, such that, let me rewrite this statement, f of p plus h equal to f of p. This lambda p you have seen is f dash p, so plus, when it will go there, it will be f dash p into h. H will multiply over here, plus eta p into h multiplied by h. I will put it rather mod h. Up till here no problem, you write h or mod h, doesn't matter, but when you will go into the general case for functions from Rm to Rm, you will have to take it modulus h. In fact, when this limit f of p plus h minus f of p upon h, h tends to 0, if and only if this limit modulus of f of p plus h minus f of p upon h. Okay. So, okay. Now, so this is our new definition. So, whenever you want to see whether a given function from an interval AB to Rm is differentiable or not, you need to check two things: whether you have a linear map, okay, whether you have a linear map defined like this and a continuous function like this, then it will be differentiable, and in this case you can get hold of the derivative as well. Let me take a simple example for this characterization. For example, consider a known function f(x) equal to say x to the power n. I will use this box characterization to see what is the derivative. Is it differentiable or not, and what is its derivative if it is. So what I will do, let me check its derivative at a point P. So let me check f of p plus h. Okay. So I am considering the function f of x equal to x to the power n. So I will apply the box formula to check the differentiability of f. So f of p plus h by definition will be p plus h whole to the power n. And this by binomial I will write down as p to the power n plus n into p to the power n minus 1 into h plus n into n minus 1 upon 2 into p to the power n minus 2 into h square plus so on, and the last term will be h to the power n. Okay. Now let me write down the right extreme side as p to the power n plus np into np to the power n minus 1 into h, and what I will do from the remaining terms, I will take h common. So this thing will become n into n minus 1 upon 2 p to the power n minus 2 into h plus so on plus h to the power n minus 1 into h. Now look at this side, this expression. You can see this term is a linear term of h because you have power 1 for h. So this is the linear term of this series. And this quantity in the bracket, if you look at it, this is my function eta p. And this is a function which tends towards 0 faster than h in the limiting case because powers of h are increasing, h square and so on. So this will tend towards 0 faster than h. So this becomes eta p multiplied by h, and therefore f of p plus h is expressed in this manner, and there is a linear term also. So the derivative f dash p must be equal to n into p to the power n minus 1, which we already know. Okay, yes, that is the derivative. So I stop at this point. I have already taken an hour or so, so we can stop.